This video looks at what a logistics function is and how to write equations for them based on information given. So what exactly is a logistic function? Well, we know that realistically, when we look at an exponential function, it's got no upper bound, but most real-life problems do. If you think about something where they have a situation where it reaches a kind of a point that it can't reach any further or kind of grow any further, like island population, eventually, you can't keep growing when you have only a certain amount of area on your island. Or the bacteria in a petri dish, or growth of seedlings, or a spreading rumor. Basically anything that has a peak value, something that it can't grow past, we have the idea that it starts exponentially, but it does eventually cap off. So we need some way to model that sort of situation. That's what we call a logistics function. It's like an exponential function with a restriction on it. So when we look at our function, we see two asymptotes here. We see the standard one that we see for an exponential function. So we see the one we've got here at y equals 0. But we also see one over here at y equals whatever this limit to grow is. So whatever this cat value that is going to be that value here. In this case, it would be 1. Now, when we write the equation, this is actually one of our 12 basic functions, but this is one we didn't really talk too much about because we hadn't really explored it before. And your book talks about two different ways to look at the logistics function. One, the basic standard function it gives you involves the value of e. And e is perfectly fine. But oftentimes it's a little confusing. So we'll look at both forms, and I'll show you kind of the one that I think works a little bit easier, and we'll go with that for our examples. But this is basically the shape of our logistics function. It looks like an exponential growth function, but then there's that cap off that kind of reaches, and like I said, we have this asymptote where this is the limit to grow. So here's our logistics function. So c, the value that we just talked about earlier, is going to be our limit to grow. Notice that in the equation, c is on the top, or the numerator here. We also have one of two forms that you can look at this equation. The way that I prefer to look at it is this first one, where you've got c over this quantity 1 plus ab to the x. The other one is involving the value of e, and that was just basically have a different denominator. It'd be 1 plus ae to the negative kx. Now, I know your book actually, when you look at some examples in the back of the book for the answers, they're probably going to give it to you in this form. But I don't think it's as straightforward as this form up here, so that's the one I'm going to focus on. A couple things I want to point out to you about this, though. You want to be really careful. When you see a logistics function, you know it's related to a basic exponential function, but the a and the b here are not the same as an a and a b and an exponential function. They are different values. A, B, and C are values that you'll be able to find from the problem, but they're not related to anything for the exponential function. And we'll look at an example to help explain this a little bit more. The other two things that you need to know, obviously, is that we're going to have two horizontal asymptotes. One at y equals 0, that's our standard one for an exponential function, and one at y equals c, that limit to grow value that we'll be able to pull out of our equation. And like I showed you in the previous screen, your graph kind of has this sort of S sort of shape to it in terms of it's kind of exponential, but then kind of cuts off at that limit to grow. This would definitely be the function that you want to get in your notes, because this is the one we're going to focus on. So if you haven't already gotten that in your notes, go ahead and do that. We're going to look at two examples. The first one we're going to look at is just a basic application, without really having to do too much besides think about our function and maybe plug a couple values into our calculator. The second one we'll look at is where we actually come up with a logistics function given information. This problem we're going to look at uses the graphical method to solve the logistic problem. So first thing we want to do is look at our situation. So we've got a population growth. The 20th century U.S. Census data, the population in New York State, could be modeled by this logistics function below. P is the population in millions, and T is the number of years since 1800. That's important to know when we think about the values that we're going to plug in to our equation. So based on this model, we want to think about the answers to these questions. Our first question is obviously going to be part A. What was the population of New York in 1850? Well, if this is my function for the population at any given time, all we need to do is figure out what T is. We can plug it into our equation. We know that it's based on the model since 1800. So if I want to find the population in the year 1850, we know that what we need to do is plug in a value of 50 into our equation. So if I plug in the value of 50 into my equation, and here's where my calculator comes in handy, I'll get the value of the population. So let's go ahead and plug it in. If I take in 19.875 divided by, and put parentheses in it if you're putting it in your calculator, 1 plus 57.993e to the, now here's another thing you want to be careful about. Just to be on the safe side, put yourself into the advantage of putting an extra set of parentheses for your exponent here, so that it knows to multiply all of this before it takes it as the exponent. So e to the negative 0.035005 times 50. If you plug that into your calculator, you should get a value of about 1.7946. Now this is obviously in millions of people, so that would be our label. So if you haven't already done that, plug this into your calculator and make sure you're getting the same value. I'll show you real quickly here what the calculator screenshot would look like for me plugging this in to make sure that you've plugged everything in correctly. Now let's take a look at the next problem. What will the New York State's population be in the year 2010? Well, again, since we know it since the years of 1800, we know that if I want to find the value for that, I need to plug in 210 years because 2010 is 210 years greater than 1800. Again, we'll plug that into our calculator, and plugging in similar to the last problem we'll do, we should get an answer of approximately 19.162. And again, this is in millions of people. So go ahead and check that to make sure that you've got that. I'll show you the screenshot here in just a moment to give you an idea of what this graph is going to look like, or what this equation will look like. Finally, let's answer the last question. What is New York's maximal sustainable population? In other words, their limit to grow. Well, the nice thing is we don't need to plug in anything to answer this question. We know that if we're trying to find the limit to grow, we can look directly into our equation. This value on the top of our numerator is our C value, and that's our value of our limit to grow. So this tells us the maximal sustainable population would be 19.875 million people. So note, this value that's on the top here, this numerator, this is our limit to grow. This is not our starting value. And again, just like we mentioned before, on the denominator of our fraction here, while it has an a plus bx, it's not necessarily the same a and b we have as in our regular exponential functions. While it's based on an exponential function, it's not. It's a logistics function. So the two are separate in terms of the values for a and b. Speaking of which, let's see if we could figure out how to write in a logistic equation given some information. So let's say we want to determine a formula for the logistics function that satisfies the given conditions. We know that the initial value is 10, the limit to grow is 40, and it passes through a point of 120. Again, we've got two options of logistics functions to look at, but I find that the easier one to work with is going to be the one that we talked about further before, and that's our f of x equals c, our limit to grow, over our quantity 1 plus ab to the x. Well, we do know one piece of information already. It tells us here that our limit to grow is 40. So that tells us that our value 40 is going to go right here in the numerator. So we can go ahead and start and say that much. Now, what else do we know? Well, we know we've got a point, an xy point, at 120, and we also have initial value. This initial value tells us something important. The initial value tells us when the value for x is 0, that the y value is going to be 10. So we actually have 2 points here, x and y. Remember, this initial value of 10 is not the same value as the value a here as an exponential function, but we do need to use those values to help us. So let's think about that. We've got two values that we can work with, 0, 10, and 120. Which do you think is going to be the easiest to start with first? If you chose the point that has 0, 10 as your first point to plug in, that's actually a really smart idea. The key thing here is that x is your exponent, and if you plug in 0 as your exponent, any number to 0 is going to be 1. So that will basically get rid of our term that has a b in it. Let me show you what this means. So we know that x is 0, and that tells us that y, or f of x, is going to be 10. So if I plug into the function I already have, f of x is 10, and that equals 40 over 1 plus ab to the x, which is 0. We know that b to the 0 is going to become 1, which basically makes this term kind of gone. It's like saying 1 times a. So we really know that 10 equals 40 over 1 plus a. This is great news because to find a is very simple now. We know that if we're going to get 10, 40 divided by 4 is going to have to be what the value on the bottom is. Well, that means that a is going to have to be 3 because if I do 1 plus 3, that's going to give me 4, and 40 divided by 4 is going to give me 10. Now we know that our equation looks more like this. F of x equals 40 over the quantity 1 plus 3 times b to the x. The only thing we're missing now is this value of b. How do you think we're going to work to find that value of b? Well, if you thought to try the other point, 120, you're exactly right. So if x is 1, f of x is going to be 20. So let's plug that in. So we've got f of x, which is 20, equals 40 over 1 plus 3 times b to the x, which is 1. So we've got a function here. We do have b. We've also got a fraction, and I know a lot of people don't like dealing with fractions. Multiple ways that you can go about doing this. I'm not going to show you every single step. I can give you a couple situations, though. If you like to, you can put this over 1 and then cross multiply and solve. That's probably the most straightforward way. But hopefully, regardless of which way that you do this, you will see that eventually you're going to get an equation that looks like this. 1 plus 3b to the first is going to equal 2. And if we solve that, you can see because the 40 divided by 20 gives you 2. So now this is pretty easy to solve. We can subtract 1, obviously, and we get 1, and then divide by 3, and that gives us that b to the first is 1/3. The b to the first is really just b, so this is 1/3. So this tells us that our logistics function is going to be the following. C, 40, our limit to grow, over 1 plus a, which is 3, times b, which is 1/3, to the x power. Please note that this cannot simplify any further. 3 times 1/3 to the x is not saying 1 to the x power. Remember, it's only the 1/3 that has the x exponent. The 3 does not have that applied. So don't try and simplify that any further. That's as far as this logistics function can go. So this would be the equation of our logistics function that has an initial value of 10, a limit to grow of 40, and passes through the point 120.